Speed's a scalar, velocity is a vector, and as such, because it's a vector, the only difference between speed and velocity is that velocity cares about which way you're going. So we use the same symbol for velocity as we do for speed, except we tack on the arrow above it, or some textbooks will just bold it and leave it like that, because it's easier to just bold a letter than it is to throw the arrow above it. In grade, for some of you it'll be Math 9, for some of you it may have been Math 10, what is the relationship, or how do we calculate speed? Maybe even the units for speed will give you a decent idea. How do we calculate how fast you're going? Yeah. How far you've gone, the distance you have traveled, divided by how long it took you to do that. And so from there, we get this, v equals d over t. And some of you may have seen this fantastic little triangle. D goes up top, v and t go right there. Velocity is distance over time. Hands up if you've seen this little triangle before. Is Liam, you here today? Cool, a couple of you. How it works is it relates velocity, distance, or speed, distance, and time. You cover up the one you want, and look, if I cover up velocity, it's equal to distance over time. And this will give you all of the equations that are relating these three variables. There's three equations for these three variables. But I digress. So that's speed. Velocity is similar. Velocity is a vector, so what velocity needs to depend on has to be something that also has a direction associated with it. Anyone want to take a guess at what velocity would then be? If it's not distance over time, it's probably going to be displacement over time. And so the differences between speed and velocity are going to have the same kind of quirks that distance and displacement did. Distances only ever add, speeds are only ever positive. If I walk to the door and come back to my desk, I will have some speed. I covered a distance, it took me a time to do that, I will have a speed. But if I walk to the door and I walk back to my desk, my velocity will have been what? 0, because my displacement is 0. So the same kind of quirks that show up for distance and displacement show up for speed and velocity, which is something we don't often think about. The equation is going to look similar. V with the arrow above it is going to be displacement, which is your change in position, delta D with an arrow above it, divided by time. But often we shorthand this and we just say that V is equal to d over t. We leave the delta off the position, and it's understood that what we mean is displacement. Your teacher is cool with this? Crossroads on your time? Okay, cool. Remember, you get your multiplication table if you have it. If you need one, on the table here too. Okay. So let's do some examples of both of these things. A person travels west for 1 hour and travels 90 kilometers. We want to find their speed and displacement. So over here, let's find speed. And I'll model how I want you to. These are simple equations, but how I want you guys to end it, as we get into the equations that get more difficult, how I want you to model this is write down what we know, write down the equation you're going to use, and then fill it in. So we know that this person travels for 1 hour, t is 1 hour. They travel a distance of 90 kilometers. And we want to find their speed. So we're going to use this v equals d over t. I didn't use the west here because we don't care about the westness, because if we're finding speed doesn't care about which way you're going. It's just how far, how long. So v equals d over t, and now I can plug it in. 90 kilometers per hour, because time is 1, 90 over 1, 90 kilometers per hour. And in this kind of question, we're not finding speed and velocity, we're finding speed and displacement. Forget that. We're going to find velocity. My bad. The only difference here with speed and velocity is that, well, t is still 1 hour. Displacement now has a direction. We're going 90 kilometers west. I still want to know how fast they were going, but now looking for velocity, we also need to include that direction. V then, with the arrow, is going to be our displacement now over our time. So that's going to be 90 kilometers west over 1 hour, which means this is going to be V equals 90 kilometers per hour west. The only difference between speed and velocity at this stage is one needs the direction and the other does not. Things become more interesting when directions change, because distances, again, they only ever add, but as soon as you start changing directions, displacements get a little bit weird. Let's do the next one. If a runner travels around a 400-meter track twice, returning to their starting position in 5 minutes, we want to find the speed and velocity here. So just so we're clear, I'm going to draw this. A track is typically an oval or an ellipse or a circle. So if this is our track, it's a 400-meter track, which means that going around it once is 400 meters. Here we are at the starting line, and a runner is going to go twice. And returns to where they started from. So let's do it all again. Time is 5 minutes, which we're going to deal with because that sucks. D is what? Sorry? 800. Twice around a 400-meter track. And we want the speed. Now, when we're calculating these things, minutes is not a unit that we use. So I'm not, now that the test is done, I'm not necessarily going to tell you, well, sometimes I will. I'll say, I want your answer in these units. But I won't always. You guys need to get into the habit now of starting to look for places where units don't make sense. Meters per minute isn't a unit we use for the speed of something. Either we're talking about the speed of something, we're talking about a kilometer per hour, or we're talking about a meter per second. So you get to choose now how we want to convert all this. You can take minutes and you can either put it into seconds or you can put it into hours. If we put it into hours, then this needs to become kilometers. So this thing needs to be either in meters per second or kilometers per hour. So the simplest way to convert this is then to do what? Yeah, let's go into meters per second. This is already in meters, so let's take the minutes and put it into seconds. How do I convert minutes to seconds? Well, we're going to do what we did before. How does this fraction get set up? We're going to put minutes on the bottom because we're going to cancel out those minutes. Seconds is going to go on top, and then the relationship between minutes and seconds is what? 60 seconds per minute. So this is going to be our time that we're going to actually use when we calculate this thing is going to be 5 times 60. Well, 5 times 6 is 30. So 5 times 60 is 300 seconds. We still have our 800 meters. So our velocity is going to be in meters per second. And so now let's calculate this thing. V equals d over t. So that's going to be 800 over 300. So what's the speed? What do we get? How quick is our person moving? I hear it. 2.6 repeating is not 2.6. If you're going to round it properly. There you go. 2.6 is going to become 2.7. I'll call it 2.67 meters per second. So that is the speed at which our runner is moving around the track. Now if I want to find velocity, velocity is a little different because velocity uses time. It uses displacement, which is a change in your position, to find our velocity. We're going to use the same time, 300 seconds. But what's the displacement now? If our runner returned to the same spot, our displacement's going to be 0. So the velocity for our runner during this time is going to be 0 meters per second. As far as our velocity is concerned, it didn't move. It's weird, but that's how it rolls. So let's do another one where the change in direction isn't quite total. We have a person. Let's draw the picture. Here's our person. Our person travels north. I'll call up the page north. They go that way 50 meters. Then they turn around and they go south 30 meters. And this whole journey takes 240 seconds. Again, we're going to find speed and velocity. So speed's the easy one. If I'm looking for speed, speed uses a distance. What is the distance traveled for this person? 80 meters. Distances only ever add 50 plus the 30. So then our velocity is going to be d over t. Our velocity, or sorry, distance is 80 divided by 240. This is a third, so I'll say that's 0.33 meters per second. Distance traveled divided by time taken. Yeah. Not often. But if you told me that the velocity is a third of a meter per second, you'll never see that, but I'll accept it. It's not wrong. It's just not conventional. In rare, like, yeah. Does that answer? Is that a satisfactory answer to that question for you? Okay. Okay, so that's speed. Let's look at velocity now. The time doesn't change. Time's not a vector, doesn't matter. 240 seconds is 240 seconds. But now, what we want is a change in position. To do that, we have to actually go look at the picture. Our person started down here. They ended at the end of this arrow. We don't care, or displacement does not care what the path looked like. All it cares about is it opens its eyes, you're right there, it closes its eyes, you yell done, it opens its eyes again, and now you are somewhere at the end. So then this is the path traveled, but what is the displacement of our person? 20 meters. Displacement is a vector, it needs a direction. From where it started to where it ended is 20 meters north. So that then is going to be our displacement. 20 meters north. So now our velocity is going to be v, the arrow above it, is equal to your change in your position divided by your time. That's going to be 20 meters north. And we don't, I'm demonstrating it now, but we're going to stop doing this pretty quick. You don't have to put the units and the direction in every time when you're calculating these things. But I'm modeling what it looks like at this stage. Divided by 240 seconds, 2 over 240 is a 12th. But that's not a fraction I ever want to leave. Because thinking about 12ths of things, like a 12th of a meter per second, that's pretty abstract for like 99% of humanity. So I'm going to take that, I'm going to leave it as 0.083 repeating meters per second, and that direction needs to come along for the ride. This is actually a lot more meaningful, because 0.08 meters is what? 8 centimeters. Person's moving this far. Well, on my paper it looks more realistic. On the screen it looks really big. On the screen it's like that. That far every second for 240 seconds is going to get them to cover the 20 meters. So speed, 0.33 meters per second. Velocity, 0.083 meters per second. Gets you to the same space, or the same spot in space, in the same amount of time. So either you could go 50 meters out and 30 meters back at 33 centimeters per second, or you could go just out at 8 centimeters per second, and you get to the same spot in the same amount of time. This is the difference between speed and velocity. One requires displacement, the other requires distance, and those are conceptually different. Questions about the calculation here? And what I'm going to get you to do is play with this. I've given you a blank space. I'm pretty sure that was a mistake, but it'll be useful for what you're about to do, because on the previous page you've got this, distance versus displacement and speed versus velocity for this map of a happy physics country. So, don't ask where this came from. It came from a physics teacher named Brad Hutchison. Sorry? Yeah. Yeah. These are weird places. You got Zorkbaum, Fizzlestein, Quatzoff, Glurknoid, Strofberg, which sounds German, and Rassissa. I always forget how many isses there are in there. So what they've done here is this is a map of roads. The distances or the lengths of those roads are listed for you there. Fizzlestein to Quatzoff, Fizzlestein to Zorkbaum, Glurknoid to Quatzoff, Strofberg, which sounds German, and Zorkbaum, also kind of sounds German. Quatzoff to Strofberg, and Strofberg to Rassissa. Rassissa. That sounds weird. The distances are all there. Distance traveled is present. The scale of this map is that 1 centimeter equals 10 kilometers. What you need to do is for these 5 paths is find the distance traveled, the magnitude of the displacement. So here we are ignoring direction. Actually, you know what? Should we ignore direction? Yeah, let's ignore direction. Make your life a little easier. We're going to ignore the magnitude of displacement. You can just tell me how big the displacement is. You can ignore direction for now. The average speed and the magnitude of the average velocity. Also ignoring direction for now. So remember, distance traveled absolutely depends on the path you take. You're following the roads have lengths, walk the road. The displacement going back to that definition, is the straight line distance. So you guys are going to need rulers that actually have centimeters on them. Not all my rulers do. Some of them are wiped out because the rulers have been used for the better part of a decade. So most of these clear rulers aren't going to work for this. These white ones will though, quite well. So I've got some rulers up here. I've got one clear shorty ruler, that'll work. Mr. DeVries has lent me these. These have rulers on the inside here, that will work. And Mr. Keeley lent me this box that has other rulers that will work. If you need a ruler from Borrow, my only request is that wherever you took it from is where it goes back to. So I gotta get back to Keeley, I gotta get a different set back to DeVries. And I want to keep the ones I have. So get the tools that you need. This is what you're working on now. Let's see how you do. Your displacements might not be exactly what mine are because you guys would have measured it between the two dots, or maybe you did the surface of the dot to the surface of the other dot. Depending on how you measured it, you're going to get slightly different values here. As long as you're close, within a couple centimeters, we'll call it good. And then you would have multiplied that by 10 and you would have got a value. So I've got distances, displacements, speeds, and velocities for each one. And for those of you who had time, I went through and I've got directions here. Take a look at those first three: comments, questions, concerns. Anyone want to go over any of that? The rain is finally here. You what, sorry? Yeah. And you walk? And you're going to get wet. Okay, comments, questions, concerns on any of those three? We're good with how we found, are you guys cool with how I did the directions? Did you get something similar? Bobby says he's good. Okay, here's the bottom two. Distance, displacement, speed, and velocity for each. And I've got my directions there. Those of you who took the time to do the directions, are you getting similar values to what I got? Lena, Liam, I know you were working with yours. Vine, did you get similar directions? Okay. But you're cool, and this sometimes trips students up. The east of south and south of east. Are we cool with how that works?
Yeah, I wasn't sure about how to write it, but I see it works better.
Okay. Okay, then if there aren't any questions, I know we've only got 20 minutes left, I am going to do the next chunk as well. It's some simple calculations. It's a review of converting some stuff which you've done already and you had a test on, so we're going to breeze through that, but we're going to take a look at this as well. So, average velocity calculation. So we looked at velocity. Now all we're going to do is take into this idea, we're going to add in this idea of average. So there's a difference between average velocity and instantaneous velocity. Instantaneous velocity is what, or instantaneous speed even too, is what your car would tell you. You're going this fast right now, which is conceptually a little bit weird because if you just freeze a moment in time, you're not really going anywhere. The averages almost make more sense to us. If we drove to Vancouver and it took us an hour to get there, we averaged, well, that's a 70-kilometer drive for an hour. Our average velocity over that time was 70 kilometers per hour, even though we weren't doing 70 the whole time. On the highway, you were probably doing anywhere between 0 and 110, depending on construction. You might stop. If you're doing 130, that's wildly unnecessary. Especially if you look at the time you gain by speeding. Like going from 100 to 110 kilometers per hour, you only gain maybe a minute, minute and a half over a 10-minute drive. No, not a 10-minute drive. It's over an hour-long drive. I think you only gain like a minute. So it's really not worth it. 130, I mean, my land speed record is pretty substantial, but again, not worth it. The average doesn't take into account, the average does take into account the fact that you may have stopped at stoplights along the way. And so when you talk about average velocities, things can get a little bit ridiculous there. Like if I told you from my front door to the Boston Pizza in Kamloops, a GPS recorded my average velocity as being 150 kilometers per hour, That would include all of the city driving and all of the time I spent at stoplights. So I shouldn't probably be recording this part, but my buddy and I did something wildly irresponsible back when we were at university, and we decided we wanted to take his new sports car to Boston Pizza and Kamloops, and our average velocity there, my driving was there, his driving was back. My average velocity there was like 145 kilometers per hour. It was stupid. Which tells you that includes the city driving and anywhere we had to stop. Which tells you our speeds were stupid. I made some dumb choices in my 20s. Nobody died. Honestly, it was a souped up Civic, and we flew. It was great. So here we go. Most important thing in these calculations is to make sure that the units match. If I've got meters, seconds, and meters per second, if I've got kilometers and kilometers per hour, this time needs to be in hours. If I've got meters per minute, which again we've already said we don't really use, but if I did have meters per minute, that means I would need distances in meters times in minutes. And if I had kilometers per day, maybe this is a turtle, our time would then have to be in days. Converting units, moving them around becomes pretty important. If units don't match, we need to convert, which we spent a whole bunch of time doing already this semester. So the conversion between meters per second and kilometers per hour, we've looked at already. What's the magic number? The magic number for meters per second to kilometers per hour is 3.6. And then depending on which way you're going, you're either going to multiply or divide. Which way is multiplying? Yes, meters per second to 2 kilometers per hour, we multiply, and then going back the other way, we divide. So if I wanted to convert, for example, 75 kilometers per hour into meters per second, all I would do is I would take my 75 kilometers per hour, and I would divide this by 3.6, and you're going to get, I'll give you these values for the sake of time, what you're going to get here is this is going to be 20.83 meters per second. So 20 meters per second is roughly 75 kilometers per hour. 27 meters per second is roughly 100 kilometers per hour, just to give you guys an idea of what that looks like. I'm going to review the factor label method for you guys here. Again, you did it on a review assignment, you did it on test, we've done it already, but I'll just review what it looks like. If I wanted to convert 306 days, and I wanted to put that into seconds, I'm going to multiply by a bunch of fractions. To shortcut this experience, I would use 3. I would use 1 to take me from days, or 1 to take me out of days and into hours, another one to take me out of hours into minutes, and another one to take me out of minutes and put me into seconds. And then I just fill in those relationships. 1 day is 24 hours, 1 hour is 60 minutes, 1 minute is 60 seconds. And I multiply across the top, I divide by everything in the bottom, and you're going to get, again, for the sake of time, I'm just going to hoof through this, 26,438,400 seconds. But again, you guys have done all these conversions for me before. So I'm going to, these ones down here that you try, I'm going to call that optional practice. If you're still like, you know what, I'm not totally sold on this, that's optional. I'll give you the answers to it tomorrow. Flip the page. Distances are the same. You just need to use the right prefixes. Again, we've seen this already. Already done, technically. So I'll do one real quick refresh, and then I'll leave this to you. This will be optional as well. If you want to crank those out, I'll give you the answers to that too. So, the one I'll do, I don't know, these are all pretty easy. Let's go, I'll change this middle one. Let's take 12 kilometers and put that into millimeters. Because that's never a conversion we're ever going to see in real life. If you're going to measure out 12 kilometers into millimeters, there is no nice conversion straight from kilometers to millimeters, so we're going to do this in 2 steps. We're going to put this first from kilometers down into our base unit. The base unit for the kilometer is the meter. And we're going to take it out of meters and we're going to put it into millimeters. And now if you recall, we had two different ways of doing this. We could use the scientific notation to replace the prefixes with their values. For example, like a kilo is 10 to the 3, so I would say 1 kilometer is 10 to the 3 meters. And I'd have millimeters. Milli is 10 to the negative 3. It's on your formula sheet. So I would say that 1 millimeter is 10 to the negative 3 meters. You could do it that way, or you could go with what we know. There's 1,000 kilometers in a meter. There's 1,000 millimeters in a meter. I'll review the scientific notation one. So I'll say that 1 kilometer, kilo is 10 to the 3. And for this one, 1 milli, milli is 10 to the negative 3. And so that thing's going to look like that. We don't like negative exponents. So what this is going to become 12 times 10 to the 3 times, and I'm going to make this a positive exponent. I'm going to flip it up to the numerator, and I'm going to take this and I'm going to put it into, make the exponent positive. So that's going to be 6 zeros, so what that is 12 million millimeters in 1 kilometer. Again, I tested you on this yesterday, so I'm hoping at this stage this is relatively easy for you guys to do. We'll find out when I mark them on Friday. So again, I'll leave these for you to play with if you want. There's 3 there. If you feel like you need the practice, do those. I'll give you the answers on tomorrow. So, average velocity problems. We're going to tweak our formula from before. Earlier we said that velocity was equal to the displacement divided by the time. I'm going to tweak this to make it the average velocity formula. What we're going to look at is our total displacement. I'm going to add this big T down here, and believe me, it's going to matter, divided by our total time. And to use what we said earlier about displacements about displacement being a change in position, we're also going to write this as our final position minus our initial position divided by, I'll say T final minus T initial. So we've got, again, now 2 different ways to approach this depending on the information in each question. So I've already modeled it once, but I'm going to formalize it here. These are the problem-solving steps I want to see. In every question I give you, I want you to list all of the given and unknown variables and match the units. I want you to write down the formula, I want you to plug in the numbers, and I want you to solve. Often, we'll include a diagram. Soon, it won't be often. Soon it won't be optional. It'll soon be mandatory. But drawing a diagram of what's happening in the problem will almost always make your life easier. Sometimes it's not necessary, like this first one I'm going to model. I'll do a couple examples, then I'm going to leave you with a little bit of homework. If I wanted the average velocity of a dog that runs 45 meters north in 5.5 seconds, I don't need a diagram for this one. You've got one object running in one direction for one length of time. So if I want to find the average velocity, I'm looking for average velocity. I know displacement, and we know time. Displacement is 45 meters north. Time is 5.5 seconds. It's the same kind of stuff that I just had you do on the previous page. So then V average is going to equal is going to equal our formula. Let's write it out. T total. And now we're going to plug everything in. This is going to be equal to the 45 divided by 5.5. And for the sake of time, I'll give you that value, 8.18 meters per second north. Because it's velocity, we need it's a vector, we need the direction. And you always need to include the units as well. If I'm marking this on a test or a quiz, that's how I mark it. That's what I want. I want to see all of the pieces. We'll say this is taking me more time than it's worth. It's in the long run, it will help you. So that I want to see you practice this stuff. When you're ready, flip the page. I'll skip to one that is let's make this interesting. Okay, so let's do a different one. Number 3. If a ball, I'm going to skip to here. If a ball is thrown at 25 meters per second down, what is the ball's displacement after 0.65 seconds? So let's write down what we know and what we're looking for. We know, in this case, we're told that the velocity is thrown at 25 meters per second down. So that now is going to be our velocity. We've got a direction there too, 25 meters per second down. For the sake of this problem, we're going to ignore gravity. We won't soon, but we are going to now. We know the time. We're told that the time is 0.65 seconds. So we've got a speed with meters and seconds. We've got or velocity rather. We've got a time in seconds, and I want to figure out the displacement. This is where that triangle I drew for you before comes in slightly handy. I mean, it's not like it's hard to figure it out, but V, D, and T. If I want the displacement, I cover up the D in the triangle, and these two are beside each other, so they're going to multiply. So the formula we're going to use to solve this thing is that displacement is going to equal velocity times time, and this is what we're going to plug everything into. Velocity is 25, and again, the units line up, so we're good. The time is 0.65 seconds, and so for the sake of this, I'll give it to you. The displacement is 16.25 meters, and we need a direction, because displacement is a vector. That ball is traveling down. So that's not a very long time, but that ball was also thrown at almost 100 kilometers per hour. So if you think about that, traveling 16 meters in 0.65 seconds for a ball moving at 100 kilometers per hour is pretty good. Do we need to do more? Should I do another one? Do I really want to force the issue and give you guys a ton of homework? No, I don't want to do that to you guys. I'll give you a little bit of homework to practice, and then I will leave you the rest for tomorrow. I want you guys to try 4. It's very similar to 3. I want you to try 5, keeping in mind that you need to unify the units. And then I want you to try these two down there. There's 4 questions I want you to try. I'll go over them. Try them now. You've got a little bit of time left before the bell goes. That's your homework, and then I'll give you some time to play with some more of this stuff tomorrow. There you go. On your mark and say giver. See what you can do with it.